welcome to another Pharma Excipients webinar. Today, we are talking about the impact of excipient variabilities on your tableting and your tableting design. I'm very happy to have two specialists with me presenting today. There is Michael Rook from TaBlitz. Hi, Michael. Hello. And there's Robert Sedlock from Natoli Scientific.
Hello.
Hi, Robert. They will present first Robert and then Michael, their presentation and the live demo of TaBlitz, which you will see will last around 30 to 35 minutes. Afterwards, like you're probably used to, we have enough time for Q&A. So put your questions like you're used to in the Q&A, and I will ask Michael and Robert afterwards all your questions. And now I'm as curious as you probably are to see the presentations. The stage is yours, Robert.
Okay, thank you. Let me share my screen here. Okay, you guys can see my screen?
Yes, perfect.
Okay, great. Thank you, Marcus. Thank you, Felipe, for hosting another Pharma Excipients webinar. I'm Robert Sedlock. I also want to thank Mike Ruck from TaBlitz for having me join him in this webinar. So again, my name is Robert Sedlock. I'm with Natoli Scientific, and I'm going to be talking to you about how to predict the impacts of excipient variabilities in your tablet design. We're going to go over some common tablet manufacturing issues, some flow issues, some powder issues, some compression issues, and how that all relates to the excipients and tablet design. So just a quick background here. So you probably know Natoli Engineering for tablet compression tooling and tablet presses. Over 50 years as a global company providing services to the pharmaceutical, nutraceutical, dietary supplements, food, and industrial industries. So this is our campus in St. Charles, Missouri, where we manufacture our punches and dies and our tablet presses. Training center, our encapsulation parts and equipment are here as well. I am located in Telford, Pennsylvania at our Natoli Scientific Group. And what we do here is provide training, hands-on training on on-unit operations from blending, granulation, tableting, film coating, and scale-up. Offering formulation analytical services, startup manufacturing services, again, training from R&D all the way to manufacturing, equipment services and strain gauge technology, and university collaborations. We work with a lot of universities around the world. Our newest collaboration is with Bombay College of Pharmacy in Mumbai, India, where we have an Natoli lab. Also, Long Island University in Brooklyn, we got an Natoli lab there. We work with other universities, Karachi, Drexel, Ole Miss, University of Maryland, and so on. I also want to mention that Natoli has a bunch of service centers. We have one in Cypress, California, Long Island, New York, and in Poland. Okay, with that said, let's move forward. So what we want to talk about is manufacturing issues related to excipient variabilities and how tablet design can impact this and help you in these issues. So some of the common issues that you're probably familiar with are flow issues. When you've got powder flow issues on an encapsulator or a tablet press, you're going to have lots of other issues. So when you've got the sticking, capping, hardness issues, and so on, I always like to determine, do you have a flow issue first? Because the way a rotary tablet press works, the compression thickness is set by the roller position. And in manufacturing, we set those roller positions, they're fixed. So if the weight is variable, the thickness is still constant. So now your compression force applied is different. So if your flow is variable and your weights are variable, your forces are variable, which can cause overcompression, undercompression, which can cause all of these defects like capping, delamination, hardness issues, and so on. So flow is one of the most important attributes for a successful tableting and encapsulation manufacturing. So flow, weight variation. You can have segregation and content uniformity issues. So you want to ensure that you're active, whether it's a vitamin or a pharmaceutical active, you have good content uniformity. Each tablet has the correct amount, okay? Static and moisture issues. If your powder is too dry, you can have some static issues and compression issues. If it's too moist, you can have agglomeration and flow issues, sticking issues, and compression issues. So I already mentioned capping, delamination. On the top right there, that first tablet there with the fracture across the horizontal plane, that's capping and delamination. That kind of fracture is not acceptable. You don't want to see a fracture across the horizontal plane. This is a tablet defect. And I'm sure a lot of the listeners here have seen capping or delamination, low hardness and low tensile strength, and chipping. Again, all these are common manufacturing issues that can be addressed through tablet design, or we're having some excipient variabilities that we have to address. We talk about sticking and picking adhesion issues. So sticking is probably the #1 tablet defect in the world, where your material is sticking to that punch face. So on the bottom right, you'll see that tool with powder stuck to the cup face. That is a common issue. That could be from excessive moisture. It could be from particle size distribution issues, and it could be just a sticky material, but not always. If your material particles don't bond to each other, they can adhere to your punch face. So you got to have good compactability and particle to particle bonding to prevent some of that sticking as well. Picking is referred to when you get material stuck between the logo. So if you've got embossing like 0s and 8s and Bs, that little island is prone to picking issues. So you can change your tablet design, engraving cuts, and pre-picks to help alleviate that picking issue. Now, another common thing I've seen is incoming raw materials. So since the pandemic, I've seen the raw material quality has kind of dropped. So when you're receiving your material from your material supplier, you want to check the quality of the material. And I'm going to show you some basic studies to assess your material coming in. So what you expect to see, you want to make sure you collected data to get the expected results. A common problem is if you don't check your raw materials coming in, and now you granulate hundreds of kilos of material, blend it, then you put it on the tablet press, and you've had these issues like capping or flow issues and so on. Now what are you doing? You're trying to adjust the tablet press settings, try to add more pre-compression. Let's slow the turret speed down. Let's increase the feeder speed. So you're wasting a lot of effort and time trying to fix these problems, but the root cause could be the incoming material from your excipient provider or API provider. So I'm going to show you some basic tests to test the quality of your incoming materials. Here's some of the basic equipment I'm going to use and show you some of the results. So an RD10A tablet press, very basic single station press, but we're measuring the compression force. The upper compression force or the lower compression force, we're measuring the ejection force, we can measure sticking force, and so on. I also have the sieve stack for measuring particle size distribution. We want to make sure we got particles within the ranges that we're expecting. We also can look at the moisture content, look at bulk and tap density, and the true density. So here's some of the basic equipment that I recommend you have at your facility for testing the incoming material to identify any variability here. You can also run this equipment with different tablet designs, as Mike's going to talk about in the TaBlitz program. All right, first thing first, micromeritics. This is very important that we understand what the micromeritics are. It's the science and technology of small particles. So we got to understand your particle size and size distribution, the shape, morphology, volume, surface area, the density, flowability, and porosity. All these basic things are very important to us moving forward before we get to encapsulation and tableting. So our raw materials, we want to understand the physical characteristics. Again, the bulk density, tap, particle size, distribution, moisture. We also want to understand the interaction with other materials. Are we going to have issues with our excipients and our active pharmaceutical ingredient? Are they going to have any kind of reactions going on? Reaction to the process. Are you doing direct compression? Are you doing wet granulation, dry granulation? So we got to understand if our raw materials can survive those processes. The consistency and your supplier. So the raw materials coming in, we want to understand all of these attributes here. Okay, particle size and size distribution. Very important to us as tablet press professionals. You don't want materials that's small and large. Let's say like marbles and sand. You won't get a nice homogeneous blend. So you got to have some type of distribution and some bell-shaped curve here. And there's different methods for measuring your particle size and distribution. I'm going to be using the sieving technique, but laser light scattering is very popular as well. So I'm going to show you how we use the sieve technique. And on the right, I've given you the sieve numbers that you might see on your sieve screen and what the sieve openings are. okay, in microns. So here's an example of a formula where we use our sieve stack with different screen sizes. And you'll see on the bottom axis here, we've got a 425 micron, 250, 180, 150, 125, 75, and anything below 75 microns. We characterize a fine particle as being 75 micrometers, and everything smaller than 75 is considered fines. Can we have fines in our formula? Yes, absolutely. Magnesium stearate or stearic acid, sodium stearofumarate, those are lubricants we add, and they are fine material, so they're going to be under that 75 micron. Colors, flavors, disintegrants, maybe some binders, they're going to be small, but we want to keep the fines below, I like below 20%. So you can have some fines, but keep it manageable below, say, 20%. If you've got excessive amount of fine particles, they're going to have trouble bonding during compaction. They might have some flow issues. They might cause sticking because if they're not bonding to each other, they'll adhere to your punch face. So excessive fines is our enemy. So here's an example of particle size distribution. How many fines do we have in here? Below 75 micron, we got maybe less than 3%. And then how much got stopped on the 75 micron screen? About 6, 7%. So this is a small amount of fines. Very nice. Here's 125, 150, 180, 250. A lot of particles got held on the 250 micron screen. This is a nice particle size distribution in my mind. Now, USP, United States Pharmacopoeia, they determine that a fine or define a fine to be 125 micron to 180, and very fine, less than 125 micrometers. 100 microns is a very nice size for making tablets. Okay, like microcrystalline cellulose, Avicil 102, or MCACell or ProSolve 90 micron. Those are nice particle sizes. But when you get to Avicil 101 or MCACell 50, those are smaller particles. We typically use those for a granulation process. I wouldn't use that for direct compression. So your final particles before tableting, we like to be above that 75 micron. So the very fine, less than 125, is not something that we use from our experience. So I just want to identify that here. Density is very important to us. Bulk density. This is the apparent powder density in defined conditions. So we pour our material into a graduated cylinder, and we measure what the mass over volume is. We like to see bulk densities in the 0.25 grams per cc or 0.25 grams per ml or higher. Obviously, the higher, the better. 0.5, 0.6, 0.7, we're getting higher. That material kind of flows better. We get below that 0.2 grams per ml. Now that material's fluffy, and we're probably going to have some issues with the flowability and getting those particles into the die cavity at high speed manufacturing. So bulk densities above 0.2, 0.25 grams per ml is kind of where we want to be. Tap density, now we're going to tap our bulk density in our graduate cylinder and measure how it compresses and consolidates. That reduction in volume gives us information about how it flows. And we'll talk about that in a little bit. And finally, the true density is the material's density with all the air removed. So if you have a gas display system like a helium pycnometer, it replaces the air with helium. And now we know the density of that material with all the air removed. Why is that important to us? Well, if we know the compressed density, which is the mass, the weight over the volume of that compressed tablet, that divided by true density gives a solid fraction. A solid fraction of 1 means we compress that tablet where there's zero porosity. There's no more air. We squeezed out all the air. Now the tablet density equals the true density. That's a solid fraction of 1, and porosity is 1 minus the solid fraction. So that would be a porosity of 0. I've never made a tablet or seen a tablet at a solid fraction of 1. I see the tablet will actually destroy and cap and delaminate before it gets there because there's no room for those particles to rearrange and move. So the tablet actually caps or delaminates. But as a formulator, this is important to us to know what the solid fraction is and the porosity. So a solid fraction of 0.8 means your compressed density reached 80% of the true density with all the air removed. 1 minus 0.8 is going to give us 20% porosity. That's kind of normal for swallowing a tablet. We want our fluids in our body to break apart that tablet so it disintegrates and then dissolves. So you need some porosity. So you want a porosity maybe in that 20%, 30%. Or if you have an ODT, an orally disintegrating tablet, and you want that tablet to disintegrate in your mouth in less than 30 seconds, well, you need disintegrants, but you also are going to have a lower solid fraction and a higher porosity, so the tablet breaks apart. Okay, so density is very important to us, understanding the bulk, the tap, and the true. So I'm not going to read all this, but this is how you can determine your bulk density. You got a graduated cylinder here, and you carefully pour the material in. Let's say you have 100 grams of your formula. Pour it in, get the volume. Mass over volume is going to give you your bulk density. Again, we're looking for above 0.2, above 0.25 grams per ml. Again, tap density is a process of tapping your material in your bulk density state. And there's a process that you can follow. It's a USP process. And when the volume doesn't reduce more than 2 milliliters after so many taps, your tap density is done. You measure that. And now you can take the ratios of the bulk density and tap density, and now we can understand the compressibility index, the CAR index, and the Hausner ratio. What is the Hausner ratio and compressibility index? Well, you take the tap density divided by bulk density, you get a Hausner ratio. Or take the tap density minus bulk density divided by tap times 100, you get the compressibility index or CAR index. So this will give us an idea of how our material flows. So excellent, good, fair, passable, poor, very poor, and very, very poor. Now, from my experience, I assess a lot of materials here for Natoli. And if I see a CAR index or Hausner ratio of poor or better, that's acceptable. I see this all over the place. So if you've got a flowability of poor, it doesn't mean you can't make tablets. It just means you might have some challenges. It means that you might not be able to run the tablet press at full speed or maximum speed. You have to slow it maybe at 50% or 30 or 20% to make sure your die has enough time under the feeder for your formula to flow into that die hole. Okay, that's called your feeder fill time. So typically about 150 milliseconds, 200 milliseconds. That's a slow amount of time for that die, or it's a very fast time for that die to fly by. So if I slow the turret speed down, I increase the feeder fill time to get that material to flow in there. So poor flowability doesn't mean it won't work. It's meaning you're gonna have some challenges. Passable and fair, great. Good and excellent, if you have that, fantastic. I don't hardly see that, but that's fantastic. Very poor, very, very poor. Now you've got some concerns. Now you have to do something to increase the flowability. You might need to granulate. You might need to add a colloidal silicon dioxide, some kind of glidant to help it flow better. Maybe the milling process needs to be adjusted, change the particle size. So very poor and very, very poor are concerning. Poor and higher is what you see out in the industry. Okay, true density, like I said, use a gas display system. This will tell you the density of your powder with all the air removed. So then you can take your compressed density divided by your true density and get your solid fraction. Okay, 1 minus solid fraction is your porosity. We need this because it'll influence our disintegration and then dissolution. Moisture content's important. You don't want our powder too dry or too moist. I typically recommend between 1 and 5 or 6%. Now, this is just a general comment. There are lots of formulas below 1%, and there are lots of formulas above 5, 6% moisture. But just a general rule of thumb, if you're below 1% moisture, you might have some issues with the particles bonding and compression. You might have some static issues as well with the powder staticky. So we like a little bit of moisture. If you're above 5, 6% moisture, now you might get agglomerations and clumping, and the material won't flow well. You might get some sticking issues, compression issues, and so on. So this is called LOD, loss on drying. There's also something called Carr-Fisher, different ways of measuring your moisture. All right, here's an example of a real product here where a customer had capping issues. And the first thing we do is we test the micromoretics. So all the things that I showed you earlier, the first thing, let's look at the moisture content. The LOD was 1.94%. We're between that 1 and 5, 6%. Okay, not bad. How about our bulk density? 0.71. I recommended higher than 0.2, 0.25. 0.71, that's pretty high. The tap density, 0.87. That ratio gave us a flow of fair. Again, fair. That's good. That's very acceptable. All right, no issues there. But look at the particle size distribution. Right away, my eyes go over to that distribution. The amount of fines in here. The material that passed through the 75 micron screen, over 15%, like 16, 17% maybe. And then look at all the ones that were retained on the 75 micron screen, over 25%, maybe like 27%. This is a lot of small particles. And then it's bimodal as well, bimodal distribution. We got a peak here, and then it drops all the way down here at the 125 micron, and then it goes back up to the 180. So this is a bimodal. Okay, so this is going to cause some issues, which was the root cause of the capping issue. So capping is when the tablet splits or fractures across the horizontal plane. I didn't even need to compress this tablet. I knew right away, here's my problem. I got a particle size distribution issue. Well, let's take a look at this next one. Well, actually, if I go back to this screen, this is the same formula, but the excipient provider provided different quality of materials, and the excipient was a very high percentage of the formula. So this is supposed to be the same formula, but the raw material came in, has some variabilities. And again, this is supposed to be the same formula, but they didn't have any capping issues with the original blend. And it's quite different. Look at the moisture is higher, 4.59%. Bulk density is a little lower, 0.59. TAP's 0.78. Flowability is good. Everything looks good, but and also look at the particle size distribution, much better. The amount of fines here, a little less than 5% here, a little less than 8%. And then we've got the particles going up in a nice curve here. This is what you want to see. This was a problem here. So right away, I knew there was too much variability in the particle size and distribution here. So now I want to compress a tablet just to kind of paint the whole picture on this product. And we follow something called USP 1062. This is a chapter 1062 in United States Pharmacopoeia. And there's a bunch of methods that they put in there. And you need instrumented presses. So instrumented single station, compaction simulators, instrumented rotary R&D presses, and instrumented production machines. We ran some studies just on our single station instrumented RD10A. And what we're looking for here is in this tabletability plot. This is the most common plot you want to generate when you're doing USP 1062 profiling. You're using pressure, compaction pressure, instead of force. Now, we're going to use force first, but the force divided by the area of your tooling gives you pressure. Why do we use pressure? Because it normalizes for the size. So now I can compare mini tablets with big, say, chlorine hockey puck tablets. If you use pressure, you can compare. 50 megapascal of compaction pressure is very low. Microcrystalline cellulose will make a tablet at 50 megapascal, but most formulas with APIs and actives won't. 100 megapascal is kind of the low end of pressures for making tablets. 200 is the middle range, 300 is the high range. So between 100 and 300 megapascal, again, for mini tablets or even large hockey puck tablets, you're going to be in that range. Now, if you're making tablets in the battery industry or catalysts, they do compress higher than 300 because they're trying to get all the porosity out of that tablet. They're trying to make a solid tablet with very limited porosity. But for oral dosage forms, where we're going to swallow a tablet, we need some porosity. So 100 to 300 megapascal is a normal range. Most pharmaceuticals are going to be between 100 and 200. A lot of the nutraceuticals, where they have a lot of actives in there, it's not very compactable, will be 200 to 300 megapascal. But again, 100, 300 kind of covers our whole range. And instead of looking at the breaking force, we originally get the breaking force in newtons, and then we convert it to tensile strength. It's a normalization of a tablet geometry. So basically, we're looking for mechanical strength between 1 and about 2 megapascal, where 1 is for chewables. It's not too hard where you can't chew it, but it's still robust enough to pass shipping and friability and handling. So 1 is our target. And 1.7 to 2 is where pharmaceutical tablets usually live. We're going to swallow the tablet. Now, an ODT or a sublingual, you might want to be in this 1 megapascal. So anyway, we're just giving you an idea from small tablets to big. 100 megapascal, 300 is normal, and tensile strength between, say, 1 and 2 is where you want to be, depending if it's a chewable or a swallowable tablet. And as we run this profile, as we increase our pressure, we want to see an increase in our tablet strength. And we don't want to level off and then get weaker, because this is where capping and delamination can occur. So not only do we want to reach our strength, but we don't want it to fall off and hit a plateau. So this is a problematic formula. This is also problematic because it never even reached a chewable tablet strength, because it leveled off, because now we're getting capping. So this is kind of what we're looking at. So summarizing, here is the original blend with a low amount of fines. Here is our new blend with excessive amount of fines. And you see the new blend had an issue with the tabletability profile. It leveled off, and now we got capping problems. And the original blend with the good particle size distribution reached the target area, and it's still increasing in strength when we increase the pressure. That's what you want. So again, this is an assessment on looking at incoming raw materials where we had some issues with the micromeritics, and it resulted in issues with tablet design. Now Mike's going to talk about how to influence tablet design to reduce some of these issues. But before we get there, last thing I want to mention, powderiometer. This is an advanced study for looking at powder characteristics. And we also developed something called a sticking index, where we can scientifically determine what type of steel type works best for your formula to have the least amount of adhesion properties. S7 steel versus chromium, M340, and so on. So Mike's going to talk about steel types as well. And here's the chemical composition of different steel types at Natoli. For example, M340 has a high chromium content to prevent sticking and releasing that product. 440C as well. Again, this is a whole chart of different steel types that can be evaluated with the powderiometer to prevent sticking. Last thing I want to mention here is CT scanning and X-ray. Is something we can use to look inside the tablet for density variation, micro cracks. So for example, this has a convex cup, and you see the micro cracks right at that area where the belly band meets the convex area. That's a density variation. So reducing the cup depth on your tablet design can reduce capping issues. So something else that Mike can do in his program here. Again, micro cracks, density variation, foreign materials, contact uniformity, and so on. So with that being said, I want to thank you for your time. I'm going to hand it over to Mike to continue the webinar. So thank you, everyone.
Thank you, Robert. Okay. Hello, everyone. My name is Mike Ruck. I'm one of the co-founders of TaBlitz. We founded TaBlitz about 5 years ago, and about 2 years ago, we brought it to market. Our goal here at TaBlitz is to create a platform that allows our users to develop an effective tablet design the first time. Today, we're going to be covering our formulation module, where we'll look at how TaBlitz is influenced by your material characteristics to predict a tablet design. We'll also be looking at how you can compare different ingredients, manufacturers, or even batches to ensure consistency in tablet performance between production runs, or define a good, effective target as a starting point for our new product. So with that being said, let's go ahead and get started. All right, so jumping to our formulation section, we're going to start off on the ingredients tab. And this is a library that I created of just ingredients that I put in to the system. So this is on my profile. You'll have your own ingredients. To create an ingredient, you'll use this plus icon. And we require different information. Everything in red is required in TaBlitz. Everything else is optional. So at an ingredient level, we don't require a particle size distribution. But we do require all this information. This is how you delineate individual ingredients. I'll tell you why that's important here in a minute. You'll add all the ingredients you require for a given formulation before you get to the formulation tab and actually build it. To collect this information, we try to help you as well by creating a data collection sheet. So you can go print this off, write down your information, take your lab results from like the equipment that Robert's going over about how you measure these different elements, and then bring them back to the platform so you can input them. All right, once you've created all your ingredients that make up your formulation, you can go to the formulation tab. Here, you can actually add different formulations or a similar formulation with different ingredients or different compositions. Again, you use the plus sign. You create your formulation by name. and then to target your compression process. Then here, you can define your ingredients from your ingredient library by searching them and defining their composition percent, the percent that they make up this formulation. From there, you can now interact with these ingredients or with these formulations, and it'll give you a breakdown of the ingredients as well as the formulation analysis that we've already run on them. Now, to run a formulation analysis in TaBlitz, you'll use this button here. But again, similar to what Robert was covering, we need information to analyze this formulation and its consistency or its risk on performance. So we give you a print off to go collect the data from the lab. Based upon those results, you bring them back to the system and you're going to enter them in. Keep in mind, we're going to be requiring you running the compression analysis to do a sampling of at least 5 tablets, because we want to take an average when we're starting to calculate our tensile strength and our breaking force information to drive our predicted compression force on the tablet we're going to predict later. So let's go ahead and run an analysis. The first section here is your dosing targets. This kind of constrains some of our AI model stuff. So our delivery method, I'm picking my target population as adults. Our delivery method is oral. Our dosage form, I'm just going to say is solid because it's most common. But you can see we support multiple here. Our coding, I'm just going to say is uncoated. Again, most common. So moisture content, as Robert was pointing out, it drives us to different reasons of why we pick different steel types, of why we constrain different geometries on the tablet design. So here, I'm just going to say we're at 5%. From a true density perspective, we'll be at 1.5. And if you're looking for information on what these things are, TaBlitz does give you a breakdown of different values you have to put into the platform. By hitting the little information icons, it'll kind of give you a guide on what we're looking for here, as well as when it comes to these analysis process. So the sieving analysis, we actually break down the sieving process for you so you understand kind of how to approach it if you're new to this. Starting off, though, we need to start off with our initial weight. I'm just going to say it's 100 grams. And then here we have standardized sieve sizes that we've just issued to you. You can customize these and create these different buckets based upon the sieves you guys utilize. I'm going to go ahead and just fill in information here. That'll make up my formulation to meet my 100 grams. Okay, now we're going to look at the tapping analysis. Again, it gives you the process breakdown, kind of steps on how to achieve the result. And then we're going to record them here. Again, I'm going to say it's 100 grams. We're going to say we're at 250 milliliters for these. Boy, can't hit that 2 button. And then 210. So we're at 0.4 bulk density, right? So we're above our 0.2. And then our tap density gets calculated based upon our tapping process, and then that gives us our CAR index for fair flowability. Okay, so we're kind of calculating and taking all that information and deducing it for you. Then we move on to our compression analysis, which again, highlighting the process here. Now, TaBlitz, we can also help you back calculate your compressed density, right? Which is your tablet density. They're the same thing. We use that. We do this by using what is called match mode. So match mode allows you to use any given tool you'd like. So we support any tool shape that we have in TaBlitz. So anything you'd like to use here, you can use. We recommend using, if you're gonna make a flat face tablet, use a flat face tool. It could be a round and go to an oval, but you'll get better results on the predicted compression force if you use a cupped configuration. If you're going to go use a cupped configuration for your final product. But for this example, we're just going to have a 10 millimeter round. I'm going to say my cup depth is 1.25. I'm going to leave my land what it is for this example. But now, where we talked about recording those 5 different sample tablets, we have our thickness and our tablet weight here. TaBlitz also allows you to plug in a different array of values to automatically average for you. So you can just plug in those 5 different sample results. So say 5.8, 5.65, and then you can set the value here, but you can see, it's going to average everything for you. You set your value, and then it'll set the value. You can do the same thing with your tablet weight. that you recorded on your sheet. You can run the average. I'm going to just say we're going to be at 380. Now, when you hit calculate, you watch tablet density here. It's going to back calculate your compressed density, which is your tablet density. And the reason why we can do this is because we understand the geometry of your tool. We understood the empirical information you collected, which is your thickness and your weights at an average. And now we can back calculate to actually get your compressed density for you. I'm going to go ahead and save this to our analysis, and you'll see that it updates here. And then, as Robert said, that gives us our porosity and our solid fraction. Now, breaking force, which again, across those 5 different sample tablets, you can run them as an average. Again, plug those in here. It'll average it for you. And we'll say we're at 14 kilopons. Okay, this tensile strength is a little bit below the 1.7 based upon the dosage form we selected, but we're going to go ahead and leave that there because we'll see how we analyze it on the other side. Now we want to record our compression force here that we utilize to make these sample tablets. This is important because TaBlitz has the ability to predict your compression force based upon the shape you're going to. So I'm just going to say we're at 12 kilonewtons. All right, now we have enough information. I've supplied all the information. We're going to go ahead and run our analysis. What this is doing is it's predicting a bunch of different tablet designs across several different common shapes, different weight slices to determine a range of tabletability properties that we're going to perceive before we even get to the tablet design process. So if I scroll up here, I can see my tabletability index. If I want to see the details of this, I'll click this little document icon, and it's going to give me a breakdown. So it's going to look at my key measurements. It's going to be my tabletability results. Notice how we have things that are color-coded to help you understand impact as well as a degree of impact when it comes to this formulation. So we have red, orange, green, right? And it breaks down here some of the different pieces of information. So Robert, to his statement earlier, looking at particle size distribution, we're at risk for segregation here. So we're saying, may want to consider granulation or the addition of glidance based upon how our distribution is on our curve. We're also looking at the moisture content here, which, we have a high enough moisture content, we're going to start looking at pre-pick and taper potentials on our engraving. Our CAR index, our solid fraction, we look at large particle sizes so we can determine your constraint on die sizes. If you're making mini tabs and your particle sizes are too large, you're obviously not going to be able to create an effective tablet, right? And we look at the amount of fines, similar to what Robert was covering earlier. All right, so now let's save this analysis. And here, what we want to do next is we want to interact with the analysis we've already run. We can see the outputs as well as the information we charted and the breakdown that we saw in the analysis. Well, what happens if I want to compare between batches, right? I want to make sure the new batch I got in meets the current batch I have in production. I want to make sure that it's going to be consistent, that when my tablet performance has the best degree of consistency, right? Or I want to compare new formulations that I'm trying to determine where a good starting point is. I want to be able to compare those two results from these tests. Well, I can do that by using A/B sampling. So this allows me to select a given formulation and its analysis that I've run. And I'll select my B over here for a different one that I've run. And TaBlitz is going to highlight for you automatically all the variations between all the measurements. It's going to give you the entire report of everything that it broke down for each of these analyses. And then you'll see the bar highlighting in the background, all the values that are different and all the considerations or risks that we identified in the platform that are different between each formulation. Well, each formulation analysis. Keep in mind, you can run more than one analysis on a given formulation. So we highlight and bring you to, a comparison between the two. So now let's move on to tablet design. And what we're going to do here is we're going to actually load in one of the formulation analysis we just created. I'm going to load in the one we just created. We're on the product tab here. So I clicked on my load formulation analysis. I'm going to go find the one I just created. I can verify the information here off to the side. I'm going to go ahead and load that in. You'll notice it set up my target population, my delivery, my dosage form. gave me my ingredients, bulk density, all the information I require to use our predictive model, which we'll get to in a second. Now, if we jump to the design tab, typically you could manually create a tablet based upon the shape you're targeting, the cup configuration you're targeting, setting all your dimensions. But we can actually predict tablet designs based upon targets. So below, something key and important, notice that our tablet density is set by our linked formulation analysis. Okay? Also notice that for the current active tablet design, the predicted compression force that I need to apply to achieve the same braking force on this volume is presented here on the production tab. And then you can run, or you can record your actual force here when you actually run this based upon the process you're using, whether you're using rapid single station or rotary. So now, if I go to the design tab and I jump into what's called guided mode, we can now use our AI modeling. And from the round that we sampled, we can actually say, okay, let's predict an oval. Now, TaBlitz has different prediction models. So we have volume, surface area. So surface area obviously allows you to target a surface area, and you'll have a resultant volume. We have ratio, which allows you to control the aspect ratio of what a tablet looks like. And then we also have die profile, which allows you to homogenize your tooling, basically predict shapes around an existing die profile, or see what your new product is. If you're, doing a CMO approach where you have, similar tooling you run for different sizes, you can predict to an array of different die shapes to see what's going to be effective shape size when it comes to our indexes. But we're going to focus on volume today. And again, my tablet density is driven from my linked formulation analysis. And I'm going to say I want a 750 milligram tablet for an oval. I'm going to go ahead and generate, and TaBlitz is going to predict for all the cup configurations that an oval has available, the different outputs for a 750 weight tablet. And then it's going to look at different index scores here. So we look at tool life, tool manufacturability, swallowability, and tablet manufacturability. Now I'm only looking at one shape, so the scores are kind of the same because the profile of them are going to be a bit normalized. And then we also give you a breakdown of each one of those indexes. But you can also here look at your predicted force, which is going to vary by cup configuration, as well as the nuances of the shape. You can also look at max compression force, which this is the max compression force allowed for that tool. The reason why this is important is to gauge of how robust your tool is going to handle your process. So if you only need to compress at 20 kilonewtons and your tool has the capacity of 80 kilonewtons, or in this case, 80 kilonewtons, obviously that's a much more robust tool. I'll get longer tool life out of it. Just something important to note. You can also look at surface area, which again, because I'm only selecting oval here, they're going to be pretty close. Outside of like compound cup, they'll be pretty close to one another. All right, now, if I want to actually drill down into what these shapes are, because we haven't even seen what these are yet, I'm just telling you they're tablets. If you select one on any one of these charts, you can interact with all of them. If you select one, it'll take you to that design. Notice we're at 2 of 6. So I can see the different designs that we have output from our predictions. Okay, so now, if I want to look at the details of each one of these and kind of their breakdown, I can see that here. They give me dimensions. Here's my 750 milligram weight, right? My resultant volume, surface area, die hole surface area. Now I can apply my design suggestion, which basically sets that as my active tablet in TaBlitz. So what that did is that now I'm looking at my 750 milligram tablet with all those dimensions, but it also updated my predicted compression force. Now, let's say that this is a tablet we've already been running, and this is the resultant of that tablet, and I want to compare what a new or a different formulation has or is going to change on this tablet. I can load a different formulation onto this same design, and notice my solid fraction, my porosity is different, my bulk density, tap density, all of these things are different here. My tablet density, my compressed density is different. Notice my tablet weight. I'm no longer 750 milligrams. On TaBlitz, to achieve that same result, if you plug in 750 milligrams here, notice what happened. My thickness increased. That's because I'm offsetting the volume to my thickness, but I'm keeping my tooling the same. What this tells me is that the compressed density of this formulation is going to be different, and therefore my thickness is going to have to be run thicker at the machine, at the press, right? What that's also going to tell me is that I have a different compression force when it comes to the predicted compression force. And this is going to give me that output as well. And then you can save these as different profiles and TaBlitz in your TaBlitz vault, so you know, based upon that analysis, what you need to run at. So I made some of these earlier to kind of show you. And these two are they're the same formulation with different batches is the simulation here. They're the exact same tooling, but they run at different thicknesses and different compression forces.